Hey y'all, so this is a video to introduce you to the idea of enthalpy. All right, now this is not too big of a stretch from what we've done before, but to get there, I want to make sure that we summarize some of the big ideas from the last two classes. All right, so here's the first one. It's all about bonds. Now, if you haven't figured it out yet, everything we've done in chemistry has been about bonds. Everything from the very first day when we were talking about electrons, valence electrons, and sharing and giving away electrons and all those things in order to form these ionic and covalent bonds. It's always been about bonds, but more specifically now. Okay, so here's the first thing. Energy is required to break bonds, right? When you have molecules, and you have those molecules that are being held together by bonds, in order to get those bonds to break so you can create something new, you've got to put energy in. Putting energy in is endothermic, right? So when you put energy in order to break bonds, that will be an endothermic reaction, all right? Now, the opposite is also true. When you are forming bonds, energy is released. So energy is released when you create new bonds. That's exactly the opposite of breaking them. So if it takes energy to break bonds, then you should get energy out when you form bonds. Now this, as it says right here, when you release energy, that is exothermic. Now this is what we've been talking about for the last couple of days, is that idea that energy coming in is endothermic, energy going out is exothermic. Now, this doesn't just apply to chemical bonds, right? This can also apply to when you have going from a solid to a liquid, right? Solid, the particles are fixed in place, and as you put energy in, then the solid becomes a liquid because you are weakening the bonds. You're not really breaking the bonds, but you are weakening them, right? And that then gives you an endothermic reaction, okay? Energy has to come in. We'll talk more about that in just a minute, okay? The second big idea that we haven't necessarily said this particularly, but we've talked about the idea is that temperature is proportional to the average kinetic energy of your particles, all right? When you say something is hot, what you really mean is that the particles in that object have a lot of energy. All right, when we talk about a solid, we talk about electrons and atoms that are inside that solid that are vibrating. They're not moving around, but they are vibrating. The amount of vibration is directly correlated to the temperature of that object. The more temperature it has, the more they vibrate. Okay, now if you get enough energy in there, then not only do the molecules vibrate, but they start to weaken those bonds and it turns into a liquid. Molecules in a liquid have a lot more kinetic energy than objects in a solid that are just vibrating. In a liquid, they're both vibrating and moving around at the same time. So liquids have more energy, right? In a gas, you're taking that liquid and completely breaking the bonds so that now the particles are all over the place. They have a lot more kinetic energy. So as you can see, that idea of it's all about temperature. It's all about having that energy. That's something that you can have. You cannot have coldness, right? We won't ever really talk about an object having cold, but it will have energy. It will have heat. It will have temperature, right? Those are things that it can have. And so the reason why this is a big idea is because of this. Hot things have more energy than cold things, right? Their particles are moving around faster. Now, why is that important? Well, this is then going to connect to this idea that gas has more energy than a liquid, which has more energy than a solid, right? That's what I was talking about in this first part, where as you put energy into a system, when you go from a solid to a liquid, you have to put energy in. A liquid has more energy than a solid does because of the particles moving around. All right, so now we've got this big idea that it's all about the bonds, breaking and forming bonds. We have this follow-up idea that temperature, that energy is connected somehow to the kinetic energy of the particles, right? And now we have a third big idea, which is this. Energy always flows from hot to cold. This is important because we're talking about this idea of temperature and kinetic energy. Energy will always go from hot to cold. It can't go the other way because cold doesn't have as much energy as hot. You wouldn't expect something that is cold to give more energy to something that's hot. It's always the hot thing that's melting the cold thing, right? So one way to consider this when you're thinking about endothermic and exothermic is this. Look at the object and look at its surroundings, both during and after the reaction. Okay? If the object is colder than its surroundings, then energy has to come in. It will go from the surroundings, because it goes from hot to cold. It doesn't matter if the object is hot or cold, it just matters, is it hotter or colder than the area around it? Because it should, all things when they sit out, when you have things sitting out in the classroom, all things are approximately classroom temperature. They're all the same, they have the same temperature. Now why would it be different? Well, it would be different if some type of reaction takes place, and if some type of reaction takes place, then it might need to bring in or let out energy. So if your object is colder than everything around it, it's going to need to bring in energy. The reason why it's colder is because something happened, some type of reaction happened that used some of the energy inside, and so now it needs to bring in energy so that it's the same as everything else again. That would be endothermic, when your object is colder than the surroundings. The opposite is also true. If your object is hotter than its surroundings, then energy must go out. If you have something that's very, very hot, the surroundings are cool, then the energy will go from that to the cool. The cool will warm up, all right? The heat always goes from hot to cold. So all three of these are very closely connected, but they all lead us to this idea of endothermic and exothermic. In which situations does it have more kinetic energy? In which situations do we need to break bonds, right? Those are all interconnected, all right? Now, with that now leads us into this idea of enthalpy, all right? Now, if you've ever heard of entropy before, this is different. This is enthalpy, all right? Now, what you can see, my definition here, the heat content of a chemical system is called its enthalpy. All right, let's rotate this just a little bit so you can see. So the enthalpy is how much heat does your system have. Now, most of the time, we're actually not really that interested in the enthalpy itself. What we're interested in is the change in the enthalpy. And that's what you can see right here. The heat that is absorbed or released by the reaction is the same as the change in enthalpy. That should make sense. If you gain heat, then the heat content of the system should increase. If you lose energy, if you release energy in a reaction, then the heat content of your system should decrease because you've lost energy. That all comes down to this idea of the change in enthalpy. And that's what we're really interested in. Now, what you should be noticing is, oh wait, when it absorbs energy, that is endothermic. Yes, when it's endothermic, energy comes in. Energy comes in, you're going to have a positive delta H. It's going to increase the total energy inside. When you release energy, then the energy of your system is going to decrease, and therefore you will have a negative delta H. We're going to talk about that more, but this is the idea for today, enthalpy. All right? Now, some of you did this in the labs last class, okay, where you got to play around with the molecules, but I wanted to show this to you for those that did not get to do that. Okay, so you can see in my drawing here, I have methane, okay, which is a carbon and 4 hydrogens. I've made a methane right here. Okay, so here's my methane. All right, I'm going to set that down just for a minute. And then I have 2 oxygen atoms. 2 oxygen molecules, each one which is made of 2 oxygen atoms. So this is them, right? And you can see how I've got double bonds holding the oxygens. If you need to review why that's the case, you can go do that. It has something to do with the electrons, the sharing of the electrons to make sure that they're both full. Okay, so this is my double bonds for my oxygens. That's there. You'll notice that the carbon-hydrogen only has a single bond there. All right, so what needs to happen? Well, if you hadn't noticed, this is a hydrocarbon and oxygen. And when you put those together and add a little bit of energy, you get combustion. And what's the result of combustion? Well, we know that the result of combustion is carbon dioxide and water. Now, if you'll notice, I cannot take these and just make them carbon dioxide and water. The first thing that has to happen is I need to break some bonds, right? You'll notice that the carbon is attached to the hydrogens, and in my products here, the carbon is not attached to hydrogens at all, right? And so I actually need to break all those bonds between the carbon and the hydrogen. So first, I'm going to put energy into my system. Break the bond, break the bond, break the bond, break the bond, all right? So now I've got my carbon, and I've got 4 hydrogen atoms, right? Because I put enough energy to break them. What you'll notice is that also over here, as I look at the oxygens, none of the oxygens are connected to each other. Before, they were all connected to another oxygen, but now they're not, right? You've got an oxygen that's connected to some hydrogens, and you've got an oxygen that's connected to the carbon. So these bonds also need to break. So I put more energy in. So break the bonds, break the bonds, break the bonds. I got those separate, and then I break these bonds, right? So I've got them all separated now, okay? So I had to put a lot of energy in to do that. That is this right here. I'm putting energy into the system to break those bonds, right? Now that they're all separated, they can reform new bonds and they can create these new molecules. Now, one thing to recognize is that we are simplifying this a little bit. It's not quite as simple as they're all broken apart and then they all join each other. It doesn't quite work that way, but you can think about that in the terms of the beginning and end, as we have this kind of middle phase where you have to break them apart first and then you can reform them. All right? So what I can do now is I can take my carbon and I can combine it with my oxygen. So I'm going to form a couple of bonds here, right? That's one of those double bonds that you see over here on the side, right here. I'll take another oxygen, I'll do the same thing. And so now I have created carbon dioxide. But in order to do that, I had to create some new bonds, all right? When I create bonds, it releases energy. We talked about that at the very beginning, right? I'm going to do the same thing here with the other 2. Remember, I had 4 oxygen atoms at the beginning, right? There's my 4 oxygen atoms right there. So 2 of them are now part of my carbon dioxide, and then the others are going to form with the hydrogens that left the carbon, and I got a water molecule there. I had to form a couple of bonds, and then I'm going to put the other 2 together, and they're also going to create water. So now I have my carbon dioxide, and I have 2 water molecules, which you'll notice that as we look at the reaction as a whole, I have the same number of carbons in the beginning, 1 carbon. I have 4 hydrogens, and I have 4 oxygens. That then goes with the balancing. That's why I needed 2 oxygen atoms here, and I end up with 2 waters there. All right? So the idea is that I need to put some energy in to break the bonds, and I'm going to get energy out when I form new bonds. Now, whether the reaction is endothermic or exothermic depends on that. Am I using more energy to break the bonds, or am I getting more energy out when they reform? That is going to be this, my enthalpy, right? So enthalpy in this situation, if you'll notice, my energy here that it takes to break the bonds is a smaller arrow than the arrow here that I'm using to show that energy is released. So what that means is, yep, I got to put energy in, but I'm going to get a lot more energy out. Now, if I get a lot more energy out, that means the net energy is outwards. That would be exothermic. My system goes from this higher level of energy down to a lower level of energy, right? Therefore, my delta H, my change in enthalpy, would be negative because the energy level has decreased from where it started, all right? Very often what we'll do is we'll use a enthalpy diagram, just like this one. Okay, it has a couple of other names, but right now we'll just go with enthalpy diagram. What you'll see is that right here on the y-axis we have heat energy. This is enthalpy, right? And then on the x-axis we have the progress of the reaction. You could also think about this as time progresses. But we're not being specific with numbers there, so we're just going to say progress of reaction. All right, so what we have here is we have some reactants. In order to get those to react, we have to put some energy in, right? You've got to break those bonds first. If you don't break the bonds, it's very unlikely that they're going to react. So we're going to put some energy in. That energy that we have to put in is often called the activation energy. As you put that energy in, your enthalpy will increase from this level up to this level because you put energy in. Now, once that happens and your atoms are separated from each other, now they can interact and create your new products. And when that happens, they're now forming bonds. And as they form bonds, you're going to drop down to a new enthalpy, right? Now, in the situation shown here, we can see that we are ending at a lower energy than the energy of where we started, a lower enthalpy. Now, because of that, that means my enthalpy decreased, which is why you can see here it says enthalpy is negative. Now, of course, as we mentioned before, a negative enthalpy is exothermic. It is an exothermic reaction because I'm getting more energy out than the amount of energy that I had to put in at the beginning. Okay, this activation energy is necessary. That's the breaking bonds part. But then as I form bonds, if the bonds release more energy than came in, this is the change in energy. This is the delta H, negative exothermic. All right, let's look at an endothermic. Why? Because we can. All right, so here is endothermic. Notice that it's basically the same, right? It's basically the same. We still start at some enthalpy. We need some activation energy, right? That's this right here. We got to put some energy in to break all those bonds. Now that they're broken, they reform. And as they create new bonds, you'll notice that this time we end at a higher enthalpy than where we started. Now, this means that we put more energy in to break the bonds than the energy that we got out when the bonds were formed. Now, that means the net energy was into the system. We end at a higher enthalpy than where we started. So therefore, delta H is positive. Energy was absorbed. Energy came in. My object now has more energy than it started with, right? Now, this, of course, is an endothermic reaction because energy came in to our system. We had more in than out. Again, you have both here. That won't always be the case, but in this situation, we broke bonds, we formed bonds, both happened. But what determined that it was endothermic was the fact that the energy in was greater than the energy out. All right? Hey, let's look at a couple of just quick, easy examples to kind of see if we can make sense of this. The first one will be pretty easy. The second one's a little bit tricky. All right? So if you want, you can go ahead and pause it and try this on your own. But we're going to practice drawing an energy profile. That's the enthalpy diagram that we were talking about. We're going to try to draw that for this reaction of nitrogen and hydrogen combining. All right? Now, you'll notice here that the enthalpy is negative 92.4 kilojoules. All right? So, let's draw our energy diagram. On this side, we have the heat energy, which is enthalpy, right? That's our H. Down here, we're going to have the time, or the progress of the reaction. Okay? We're going to start with a certain amount of energy. This is how much enthalpy there was at the very beginning. Then, in order to get this reaction to happen, we obviously are going to have to break the bonds holding the nitrogens together and the bonds holding the hydrogens together. So we're going to put some energy in. So we're going to put some energy in just like that. That right there is what we call the activation energy, the energy we need to get this game started, right? And then we get up there, and then they're going to reform, and I know it's going to go below where I started from because the enthalpy is negative. So my enthalpy went from here down to here. So the change in enthalpy is negative. I still have heat energy, so my enthalpy is not negative, but it is lower than it was before. So this right here is the activation energy, and this right here is the delta H. That would be the change in the enthalpy of negative 92.4. All right, so you can see how we can draw that just knowing this idea. We know that the energy to break the bonds is going to be less than the energy that we get out when these bonds are formed. Okay, now let's look at one more. I told you the second one would be a little bit more tricky. It's not hard, it's just a little bit more tricky. All right, so here, let's have a look. Notice that this one is simply H2O solid, so ice, turning into H2O liquid, water. So we got ice turning into water. And notice that the delta H, the change in the enthalpy, is positive. That should make sense. In order to get your ice to turn into water, you need to add some energy in. You should already know this is then endothermic. The last one was exothermic because we got more out. Okay, but this one will be endothermic. Let's see if we can sketch our energy profile, the enthalpy diagram. So we've got our heat energy over here. And then we've got our time down here. So our ice has a certain amount of heat energy, right? And then it shows, obviously, first we need to weaken those bonds. So therefore, it's got to go up. All right? Now this is why I said this one is a little bit tricky, because in this one, we're not going to form new bonds, right? The bonds are already there. They're holding the water together as ice, and we're just weakening those bonds. And so really, this one is not going to have a hump. It's just going to flatten out like this. You'll notice that we still have a delta H here. This is the change in my enthalpy. The enthalpy ends higher than where it started. So that would be my plus 6 kilojoules. Now, if you do something like this where you went up and then went back down a little bit, that's fine for now, as long as you make sure that it ends higher than it started. Now, long run, we do want to make sure that we're recognizing when we're creating new bonds and when we're not. You shouldn't come back down again if you aren't creating new bonds. Remember that energy comes out when we form new bonds, not any other time, okay? So in this situation, we just weaken those bonds, put energy in to do that, and then it flattens out, okay? All right, that's it. I hope that was helpful for you. I hope that it made sense as you start putting some of these ideas together with the bonds and the energy and the exothermic, endothermic, and finally our new term, which is enthalpy and the change in enthalpy. Remember, the change is more important than the value of the actual enthalpy, all right? The change is the most important thing, okay? All right, that's it. We'll see you next time for some practice.